Hi, everyone. Can you hear me? Oh, great. Thank you. Sorry about that. So welcome to the IETF 802 virtual meeting. And my name is Juan Carlos Zúñiga, and Wasim, my co-chair, will be your hosts tonight or the morning. So the virtual meeting tips, of course, this is a new for us, but still a few common things. If you're difficulty joining, just try the call-in option, but I guess if you are hearing me, then you're fine by now. I'm going to ask you to mute your mics if you're not on the queue. By now you should be familiar with WebEx, and you can join the queue. You can remove yourself from the queue. You can participate. All those buttons are on the left top of your screen. You're going to be added to the blue sheet automatically, so no need to take care of that. And the Jabber is actually via the IETF data tracker meeting agenda. So as a reminder for IETF, this is an IETF official meeting, so you are aware of the IETF processes and policies, and that any IETF contribution or participation in this meeting is covered by those policies. If you ever have any questions or you want to see more details, there are some links here on this page. As a reminder, we are taking minutes. The meeting is being recorded. Your presence is logged. If you want to contribute to the online minutes, please do so through the Etherpad that you can find the link either here or in the meeting materials. The recordings and minutes will be public, and make sure well, again, the blue sheets are already taken care of. We're going to be taking notes, and Wasim is going to help with the JavaScript, but my understanding is that actually you can also do so directly through Meetacle. So our agenda today, we're going to start by giving a quick update on the work group items. Then we're going to move to the SOX protocol with Vlad, the Internet Protocol encapsulation with Ian, AX25, and an intro to the SHIC LP1 protocol, the recently published RFC 8724. And Pascal is going to talk to us about how we can use this SHIC protocol over PPP. So is there any bashing for the agenda? Okay, I'm seeing a comment there from Dave that there's an issue with the note. I previously clicked and I had the same issue. I don't know if that's normal. So as a backup, we might be taking offline minutes and uploading them later on. All right, so hearing no comments about the agenda, we can move to the working group status update, where we have the discovering provisioning domain names and data that has not been finalized, but it's already in auth 48, so it should take no time before it becomes an RFC. Then IP fragmentation considered fragile, with already in the RFC editor queue. And the generic UDP encapsulation, the GUI draft has been submitted to ISG for publication, and it's in AD evaluation. So I don't know if Eric, you want to give us a quick update about that?
This one it's still in my queue, so we'll go further, most probably before end of this summer.
Excellent, thank you. Great. So with no other points, maybe we can move now to Vlad's presentation on the SOX protocol version 6. Vlad, are you connected? If you are, you can share your screen.
And by the way, JC, Who is the note taker right now?
It's going to be me and Wasim together because it's we have this issue with the Etherpad.
Okay, the Etherpad is running, right? So task commit or something like that. You need to click on the button where it is two pages next to each other. Then you can edit.
Oh, okay. Thanks for that.
I'm trying to edit it at this time. I'm doing what I can, but.
Oh, thank you very much, Pascal. Very much appreciated. Okay, so we have Vlad in the queue, and I'm letting him share now. You may need to click on your mic to be able to speak. The little icon. Okay, let's see. We can still not hear you.
How about now?
Yes.
All right. I can't see my slides on the screen.
No. I allowed you to share.
So do I have to share my screen?
Yeah. If you click on the camera button, it should tell you if you want to share the whole desktop or one application.
Okay. Just give me a second.
It's actually on the display icon.
Should I just have to bring up my slides. Okay, can you see my screen now?
I'm accepting it now, so it should come soon. Yes.
All right. So, hello. I'm going to give you a quick update on the latest work on SOX v6. So these last few revisions have focused on the UDP Relay. We have added all kinds of features in order to bring it up to parity with Turn. And in fact, the current functionality supersedes that of Turn. We have more features, and I hope we haven't omitted anything. If we haven't, then SOX should be more feature-rich than Turn, and it should also be somewhat easier to use. And we've also added support for ICMP errors. We'll see more on that later. So first up, we've refactored the messages used by the UDP Relay. So the old messages, the association initialization, the association confirmation, and the datagram messages still have the same semantics. We've just refactored them, and they all share the same header that you can see on the left side now. Notably, we've added a message length to all of these relay messages, and this is somewhat useless when sending these messages over UDP, but it's crucial when if you want to send them over TCP. So now, clients that don't have access to UDP or DTLS can send the messages over TCP. They can fall back. So TCP or TLS is now a fallback mechanism for the UDP relay. We've also added error messages. We'll talk about that later. So let's talk a little bit about supporting ICMP. So fundamentally, ICMP is a protocol that offers diagnostics for layer 3. The SOX protocol abstracts everything from layer 3 below. So there is no straightforward way of supporting ICMP with a simple mechanism that fits all ICMP messages. So in particular, there are two kinds of ICMP messages. We've got echo and echo reply, which are not supported in the current version. They have arbitrary payloads and are very similar to UDP. The ICMP messages that we handle now are ICMP errors. This is a they are partially supported, and this is an optional feature. The reason why it's optional is because of implementation and deployment concerns. So in order to catch ICMP messages, you need to use raw sockets on Linux or other Unix-like systems. And the proxy also needs to run as root. Obviously, that can cause problems for some people, so it's not a core feature. Now, in particular, the ICMP errors that we particularly support are network unreachable and host unreachable, TTL expired, or packet too big, which is a new feature in ICMP v6. The other ICMP errors don't really it doesn't make any sense to support the other ICMP error messages, and some of them are outright none of the client's business. Also of note is that the client cannot instruct the proxy to issue any kind of ICMP messages. So it makes no sense for the client to go like, hey, Mr. Proxy, please tell the remote host that I am actually unreachable. That makes no sense whatsoever. So ICMP errors are only relayed from the proxy to the client and not the other way around. So translating ICMP errors is rather straightforward. So on the left, we've got the SOX error message format. And on the right, we have an ICMP error message. So we'll discuss the fields in the SOX error message shortly. So the ICMP error is exactly what you'd expect. You have an IP header. Layered over that, you have an ICMP header, and the ICMP payload contains the packet that supposedly was the troublemaker. So you've also got an IP header and the UDP header inside. So first up, the packet that supposedly caused the error was issued by the client. So if we look at the inner packet source IP and the UDP source, we can tell what association ID was corresponding to that source. Conversely, the destination IP and port are placed further down in the error message. And finally, with the IP of the host that issued the error message is dubbed the reporter address in the SOX vernacular. So that IP and the ICMP type and code are encoded in the SOX message. The error codes, of course, are separate from the ICMP error codes, but there are error codes for each of the supported ICMP errors. So that was rather straightforward. We've also added some other stack options for UDP-related use cases. So you can now fiddle with TTL that allows you to implement some kind of traceroute utility over SOX. This was a bit of an oversight, but we didn't have the functionality to set the IP don't fragment bit. You can now set the DF bit. And there's also some option that enables you to control the port parity. The RTP, some RTP implementations are rather picky about what ports they run on. They would like to run on 2 consecutive ports, and I've added an option to SOX that kind of handles that. I won't go into details, but you can look at the draft if you want to see more about that port parity option. So now I'd say that the SOX draft is rather mature. Most of the functionality is there, but it still requires polish and nitpicking. We've tried to handle all of the new use cases that have cropped up and that have led to to the creation of non-standard proxies. So in particular, Tor uses some non-standard extensions, and ShadowSOX also is non-standard in that it makes liberal use of MPTCP and TFO, where it might be problematic sometimes. And the UDP Relay has been revamped so that it's much more usable. And that's about it for me. So would you like to work on SOX v6 in the INTAREA workgroup?
Thanks, Vlad. So yes, this is a draft that has been presented several times. We've had multiple comments and positive feedback. So it's about time to see if we can make a call for adoption in the group. So at this time, maybe I will ask you to test the humming tool, which is the little graph bar on the left top of your screen. We have Peter. Oh no, probably not. So we're going to make a hunt for adoption. So those who believe this draft should be adopted by the working group, please hum now.
Should I also hum myself?
Yes, please.
All right.
I'm not sure that the voice hum will make it into the tally, but it's still worth it. Okay. Okay, so we got a forte for that. Thank you very much. So it seems like we have support for adoption. We will confirm anyway on the list.
And GC, can you ask the other questions? Who would oppose the adoption? And again, it's the mailing list is deciding, just to get a test.
Sure, no problem.
Thank you.
So all those opposing the adoption of this draft, please hum now. Or not. Okay, so we got a pianissimo for that. Thank you very much. So we'll do confirmation on the list then. Thank you very much, Vlad.
Thank you for having me.
Thanks. So we're going to move on now to Yain's Learn Mod. Okay, give me 1 second. So you're able to share your screen now. Can you share your slides, Ian? Okay, we can see a weird mirror effect, but we can see your screen. In order to speak, you need to click on the mic with the little play button on the left, top left. We cannot hear you yet. Okay. Okay.
Hello.
Yes, we can hear you now.
Okay, cool. And this.
If you share your slides now, or you put them up, you can. Yeah. Perfect.
Okay. Hi. So I'm going to talk about something which might be quite foreign to many people, and it's a very niche sort of protocol that exists within amateur radio. It was defined a while ago. The latest revision was around 1998, and it's something that's stayed alive within amateur radio, and I'm working on at the moment. So for those of you that might be unsure as to what amateur radio is, it is a very, very broad topic that mostly it's a radio service that's run by amateurs. And the main difference between amateur radio licensing and the licensing of, say, your mobile phone is your mobile phone is a device that has a license to transmit on a set of frequencies. But with amateur radio, it's the operator that is licensed, and they're judged to be competent to operate radios in various ways. I can't see my camera, but I do have some props, so I'm just going to wave them in the general direction of the camera and hope that I'm getting it right. So this is a typical amateur radio, and here there's a microphone attached, and you might be familiar with maybe depictions in TV or movies, and you see someone talking on the radio. I'm going to take the microphone off of that because I'm talking about packet radio. And what I have here is a packet controller, and you might have memories of dial-up modems, and this is sort of the same thing. It's going to connect into the radio, take audio out of the radio, put audio into the radio, and essentially play modem tones over it. And this is where AX25 comes in, which is a link layer protocol that's used by radio amateurs. And the main reason that it's kept its popularity is in place of link layer addresses, we use amateur radio call signs. And all around the world, you have a requirement that amateur radio transmissions are clearly identified. So by embedding the call sign into the header of every packet, you get to meet this requirement. And it also has seen implementation for decades now. So there's a network effect to using it compared to going off and doing your own thing. So the packet controller I showed there uses Bell 202 tones and works over an FM radio. And there's an abundance of FM mobile radios that have been discarded from taxis or other vehicles. So it's a cheap way to put together a packet radio station. For marine applications particularly, but also if you're away from infrastructure, there's also people will use Bell 103 tones over the high frequency bands. And there's been other experiments with different modulations. But what I'm talking about today is none of these physical layers, nothing that's actually touching a radio. I'm talking about running AX25 over IP as an overlay network to link together amateur radio sites. There's a number of applications that you might run over AX25, bulletin board systems, mailboxes, keyboard to keyboard, where you just have a chat between two stations and you are typing messages to each other, kind of an instant messaging. There's standards for running IPv4 over AX25. There's been recent experiments with delay tolerant networking. When you're running at 1200 baud, the time it takes to get the packet out of the interface is a considerable part of the round trip time. And there's also systems like the automatic packet reporting system, which are built on top of AX25 to create something that's sort of like a real-time tactical data link. And analogs would be link 16, link 22, ADSB, or AIS in the marine environment. And you have now special purpose-built. So this is an amateur radio that's designed for mounting in a vehicle, takes a GPS antenna, and can report positions via packet to others around. And then they also have a handheld version of that. So there's wide support. This equipment's still being manufactured, and it's in use around the world. What I'm talking about in this presentation is an update to RFC 1226, which very simply described how to encapsulate these frames within Internet Protocol. This assigned a protocol number to it, but didn't really give any recommendations as to how you would deploy this. And so the draft that I've put together adds considerations for quality of service and also security considerations, which at the time that this draft was written, I think security considerations were very low on the priorities. For quality of service, I've looked at the deployments of these links that exist in the internet at the moment. And you're mostly looking at linking between two sites that have RF, and then you have an internet backhaul between them. And in some cases, the internet backhaul may be, again, an amateur radio link using 2.3 gigahertz modified Wi-Fi equipment instead of going through an ISP backhaul. It's still an amateur radio link, but it's now higher speed and it's a IP link. So I've looked at the applications that are used and come up with these code points. And I've also taken a look at some research in this area, and just to make sure that as it passes through equipment, there's not going to be any priority inversion occurring. These are recommendations because they're not musts, because depending on the deployment scenarios, you might want to change these around. And usually these are not inter-domain deployments. They are negotiated between two radio operators, and they are talking to each other, so that they can change these things if they want. The security consideration section, the integrity check is included in the original protocol. There's a CRC check that's included at the end of the AX25 frame, but there's no authenticity guarantee. And the FCC regulations, as well as the regulations in the UK, require that you ensure that only licensed radio amateurs are allowed to operate a station. If a packet comes in and that's transmitted onto RF, you need to have some way of validating the source. And at the moment, those guarantees are very weak. Also, possibly unique to amateur radio, encryption is forbidden. In some cases, it's a crime. So using encryption is not a way of satisfying the security considerations. So the recommendations in this draft are to use IPsec with ESP and use null encryption. The reason that we're not recommending AH, the authentication header, is just because ESP has been implemented in places that AH has not been implemented. And in order to have interoperable solutions, it's best to use the thing that most things are going to be able to speak. So that's all I've got really on the draft. It's not a very long draft. But if there's any questions, comments, feedback, I can provide some answers.
So thank you very much. That was a quick presentation. I don't know if you were transmitting over AX25, but you were a little choppy.
Oh dear.
But fortunately, you know, it was very graphical and very descriptive. So if we have any single question, because we are short on time, we can take it quickly. Otherwise, I would encourage people to send feedback on the list. We've already seen some feedback. I mean, this draft has been going around for a couple of months at least, and we've had some interesting discussions. So please continue the discussion on the list. All right. So thank you very much. Yeah, very good.
Okay.
We can move to the next one. Dominique.
Can you hear me?
We can hear you now.
Great.
You want to share your screen?
Yeah. There you go. Hi, everybody. So this is a presentation, an introduction to the static context, header compression, and fragmentation, nicknamed SHAKE, that was recently standardized under RFC 8724. And
Dominique, we can see your audio, sorry, your video fine. Your audio is a little choppy, at least on my side, although I'm not sure if there's anything you can do about it. It's probably a codec issue, because the volume is fine, it's just that it chops from time to time.
okay, yeah, I heard that from the previous speaker as well, so I don't know if it's system-wide or just me, or maybe too close to the mic. I'll move away a little bit. Okay, is that better?
And the audio seems to be fine. It's just that from time to time it chops parts of your speech. So be aware.
Okay. Maybe I was too close to the mic in that rating. I'll try to be a bit further away from the mic. Okay, so LP1s, if you want to read an RFC about LP1s, there was a summary of the characteristics. The common characteristics is the very low data rates in the hundreds of bits per second, or up to a few kilobits per second. Some of them, as shown here, are 0.1 kilobits a second, 100 bits a second, and also the small payloads that are allowed, typically a few dozens of bytes. Compare that to IEEE 15.4, the WPAN networks, which have payloads more in the hundreds of bytes. Also, a very high impact of transmission on battery lifetime. These are primary battery operated, and also because some of these systems are on unlicensed, and there is a regulation on time layer duty cycle, and so if you have too much transmission going on, then you have to shut up for a while until your 1% duty cycle is recovered, for example. Also, LP1s, it's one device talking directly to a network gateway or base station, whatever you want to call it. Also asymmetric links for different reasons, but the duty cycle limitation being IETF. There's a long history of header compression. And Anna, one of the co-authors, has studied ROC extensively. And we've also been around when 6LoWPAN was designed. And compared to ROC, which is has a dynamic context and needs feedback, links, and it works because we assume that IoT devices don't change their applications too often.
Dominic, do you hear me? Because your voice is very bad, so maybe I can make comments on your slides and you continue to share it, if it's better.
Okay. Okay, sure.
Okay, so I just make some summary of what Dominic said before, is that we are working on LP1 networks, and LP1 network are very, very low network with lot of constraints. That's why we had to develop a new... can you keep the size? So I don't have the slides right now, so we develop a new compression mechanism that is used for these LP1 networks. So one of them is LoRaWAN network. You have also Sigfox and also IEEE. And so this compression mechanism is quite original and differ from the previous one, but of course take also some content from 6LoWPAN or ROC and Van Jacobson. So the goal is, yeah.
I'm going to share the slides. Just let me know that if I should move further or back.
Okay, that's good. So the compression mechanism is called SCHC, S-C-H-C. So it's a static context header compression. You can go to the slide you showed was good. This one, yes. So it has recently been issued as an RFC, and it's called stateless. It means that you maybe the next slide. Can you show it? Next. Okay. How the compressor? No. The previous way. Okay. How does it work? It's we have a library with a lot of packet description that we call rules or card in this example. And when the packet arrives to the compressor, what we do is to check among all these cards to see the one that produce the best compression. And when we have found it, we send the card number, some compression residue, and the rest of the packet, the data. And it arrives at the other side, which must have the same list of cards of rules. And from the list of rules, it can reconstruct the packet. So next slide, please. So here is an example of rule that is taken from the RFC. So the rule, in fact, is a list of fields. So it's something very generic, but we don't specify IPv6, UDP, CoAP, or anything. But it's a generic mechanism, and then it's applied to protocol. So the first four fields: field ID, field length, field position, and direction indicator, are used to classify a field. And then we have an expected value for this field and a matching operator. So we compare the target value with the field value using the matching operator. And if all the fields of the rule match all the fields of the packet, then we can apply a compression. And the compression is described by a compression-decompression action. And the compression action can be send nothing, send the field integrately, completely, or send just some bits, or we have an index with a list of value, and we just send the index. On the opposite side, we do the opposite using this word. So next slide, please. So here you have an example of the compression rule that is defined for IPv6 on UDP, and you have on the rightmost side the number of bits that is sent for IPv6 on UDP using this word. This works also well for co-op, but I don't go into much details here. So next slide. We have also a fragmentation mechanism that use all the property of LP1 networks. It means that we, for example, so in LP1 network, you have a downlink that is very limited. So we use a bitmap to have feedback, and this bitmap tells you which packets are well received and which one has not well been received. And we have a very efficient mechanism that is called Acon error. And Acon error can reduce the feedback to one message if you have no errors. And of course, the number of feedback increase when the number of error increase too. And we have NOAC, which is very simple. We have no feedback, but when the packet is received, we are sure that it's correct or not. So next slide, please. So here it's what I said before, is that SHIC is a very generic mechanism that describes a generic compression mechanism, a generic fragmentation mechanism, and then we have to apply it to some environment. So the first RFC describe how we do UDP and IPv6. We have described how to do co-op compression. We are working right now also on ICMP compression. And we also apply it to different environments. So one of them is LoRaWAN, the other one is Sigfox or Narrowband IoT, and Pascal will present a way to adapt this to PPP, point-to-point protocol. So next slide. If there is. No, okay, thank you.
Okay, so thank you very much. Laurent, if you have any questions, as you can see, this is a generic document that has been already approved and published in the LP1. And the idea is to present here the concept, because Pascal will now talk about how to apply the same principles to non-LP1 technology. And that's why we need to understand at least the principles before understanding what Pascal will want to share with us. So. Okay, so I guess because we are running out of time, maybe we can move to Pascal. Hello, Pascal. Do you want to share your slides, or you want me to share? We cannot hear you. You need to click on the mic.
So I placed myself on the video queue, but I didn't know whether that gave sound or not.
No, now you have to click on the little screen, like a monitor, and then you can share your slides.
Okay.
Yes. That
do you want to share them, or do you want me to share them? Okay, I can share them. Let me share them.
Yeah, it seems like you have good bandwidth. So let's see.
Okay, so actually I've added one slide just as a helper, so I'll go quickly through it, but you won't find it in the PowerPoint that I uploaded. So there we go. So you've seen that we have this new compression scheme, SHIC, and it was initially designed for low power wide area networks. But as you know, there is all the world of existing legacy links, like, for instance, GPRS.
Sorry,
or.
Well, I cannot see your slide yet.
Oh, I said share. I'm supposed to share my screen. Oh, there was. Firefox cannot grant a permanent access.
Okay, Firefox.
Okay.
I know some browsers allow you to share just a specific application, and some don't, probably. So
yeah, it doesn't seem to.
JC, may I suggest that you share the slide again?
Yes, can you please share my slides?
I
Because
just don't have that
Firefox doesn't
latest
seem to
version.
want it.
But I'm not sure I have the latest version, Pascal. Pascal, if you can send me the latest version, I can share.
Hello?
Hello?
Can you use the one you have? It's okay. I think it's fine.
Okay.
I just added one slide for context, but we won't have time for it anyway, so I'm very happy with what you have.
Can help here because I'm not able to find quickly the latest version, any version that matter.
Okay, let me try again.
Just apparently
Share.
corrupt. Okay.
Let me try this. Yes. I can select it. Okay, it seems that I could share it. I cannot share the full screen, but apparently I could share my slide. Do you see it?
Yes, go on. We lost your audio, Pascal.
I'm sorry, it goes on, goes off, and I can't say why. Okay. So basically, we have enabled SHIC for LP1, but there's a huge variety of links for which SHIC is not enabled. And there was a quick and easy way to enable SHIC on all those networks is to enable SHIC over PPP. So it's a good idea for two reasons. The first one is there are already compression schemes defined for PPP. So there is all the mechanisms in PPP to say which compression you're using. And the second thing is PPP gives us all the legacy radios like your GPRS phone, but with PPP and serial links, obviously. But with PPP OE, you can get anywhere. I mean, with Ethernet, you get Wi-Fi, you get pseudo wires, you get everything. So basically, we thought that the shortcut to get PPP over foo was to get PPP over PPP, SHIC over PPP, and then do PPP over foo. So we started the work at LP1, did some review there, but at some point we talked with Eric, and the decision was that LP1 was not chartered to work on PPP, so we better talk at INTAREA, and that's why we're here now. So we moved the draft to INTAREA and proposed it there, and Eric, maybe at the end, if you want to, I have a discussion if you want to say more words about this. So basically, this is like a 0.0, but it's not really because there were two instances in LP1 already. So the changes basically are that I provided more parameters, and basically SHIC is completely stateful. So you have to say where the compression state, which tells you which bits go compressed and which don't. This must be stored somewhere and available to both parties, the compressor and the decompressor. So as we extend PPP to express that SHIC is the compression mechanism, you need also to express the way to locate this compression data. This is the slide which puts things in perspective. So as you see, you may have a device which is not aware of SHIC, in which case it's on the left, it's what I call the speaker, in which case the router will be doing the SHIC compression, but the two devices on the left could be collapsed in one single device, which is the PPP client. And in the example that I'm giving, it's PPP over Ethernet. So we have an Ethernet network, meaning if we have Ethernet, it can be pseudo wire over the WAN, it can be Wi-Fi, it can be VXLAN, it can be anything. So if you have split the speaker and the router, then the router needs to determine what the speaker is and get the compression state, and that's what the first arrow tells you. Then the next steps that you can see are classical PPP over Ethernet. It's just that when we will be doing the IPv6 CP negotiation, we'll have to place this configuration request. Well, in the configuration request, we'll have to place this option 2, which is the IPv6 compression protocol description. And in this, we are actually adding the capability to say, oh, the compression is going to be SHIC. And since there is already in the RFC the way to express some data which is specific to this compression, the data that we propose to use here is the URL of the compression state. So the router or the switch that acts as a gateway will go and fetch the rule. If it's happy with the rule set and could parse it, then it will send a configuration ACK, which will begin the IPv6 traffic over this particular session. So the discovery, which is part of the step defined by PPPoE, in PPPoE, it's a sequence of 4 pad message, PAD-I, PAD-O, PAD-R, PAD-S, and they could be replaced by anything. We don't necessarily need the pad message from PPPoE to find which are the two ends, the compressor and the decompressor. But it's just a logical option when you're using PPPoE. So here I'm putting the resulting packet, and this is an IPv6 over PPP packet, but at some point you see, so the PPP protocol is 57, meaning IPv6, and then after that you can see instead of the normal PPP packet, you see the SHIC rules, which in the profile that I propose is expressed in 2 bytes. Compression residue and padding, which I placed there to simplify, and then we can discuss with the SHIC people if it's a good idea or not. And then whatever uncompressed original payload that could be after the compression residue. Note that can also be uncompressed payload inside the compression residue, right? And so that's basically it. Half of the document is probably, and maybe the biggest half, is to propose a profile for SHIC over PPP, and for this we need the skills from the LP1 group, from Dominique, Laurent, etc., to tell us that this profile is okay. And in particular, the profile doesn't have fragmentation because we expect high-speed links mostly. And then the game is
stopped. Sorry, we are going to have an abrupt stop in less than a minute. So.
Okay, so let's move to the question basically. So in less than 1 minute, Eric could tell us why we should do it and whether we should adopt it there, and then the next question will be for the mailing list, I guess.
Yeah, so basically the responsibility for LP1. This specific work was impossible to take into account in LP1 because the chart of LP1 is only for 6-4/1 and basically LP1 layer 2 networks. So the catch-all working group is really INTAREA here. And there's a reason why with the chairs of LP1, Pascal, and the chairs of INTAREA, Wassim, and JC, we propose that this document is adopted here. You're muted, GC.
We're going to be cut very soon, so please send your comments and questions to the list. There were a few on the chat, but we don't have time to go through them. So I encourage you to please ping Pascal on the list about this document, and for sure we're going to keep talking about it over the list and over the next sessions. So before we're cut off, thank you everyone. Sorry about the little hiccups, but thanks a lot for attending this session. And I wish you all a good IETF virtual meeting week.